Hey everybody, welcome back. Um, in this video, we're going to start chapter 18, which is confidence intervals for a population proportion. So if our P or our population proportion is unknown, then what do? We can no longer use those formulas, right, from chapter 17 to find out the average value of our sample p hats and the standard deviation of our sample p hats, right? The formulas for those involved our population proportion, which we will see in the next slide. So if we don't know our population proportion, which is usually the case, right, in statistics, you don't know something about an entire population of people or things, and you want to find out something about the population, right? Whether it's the average or the proportion that they have some trait, or if they don't have some trait. Um, but the idea of statistics, right, is to take a sample from your population, and then to use those statistics to then tell you something about your population, right? So this is kind of the normal case in statistics. You don't know about your population really at all. And we're taking samples and using statistics to tell us about it. So one of the things we can do with our statistics is calculate something called a confidence interval. And this gives us an interval or kind of a range of values for our population parameter, in this case, our population proportion. Right, so before, like I mentioned, the standard deviation of p hat was using the population proportion, right, times 1 minus our population proportion over n. The average of all of our p hats also, right, was the average of all of our sample p hats was also equal to population proportion, right? We would be given this value, and so we knew where to center our normal distribution of sample proportions right at P. But now we don't know where P is. We don't know where our sample proportions are centered around. Um, and in practicality, right, we can't take all of the samples from our population, right? It would take too much time, too much money. By the time we took every sample possible from our population probably would have changed, right? And our data would be out of date. So now instead of using that population proportion in these formulas, right, the Z formula also used the p hat minus the population proportion, divided that by the standard deviation of our p hats, which again required the population proportion. Now we're just going to use p hat in place of these population proportions down here for our standard deviation. As we can see here, right, we'll just say, okay, we'll estimate the population proportion, right, with its sample proportion, its estimate. So now p hat times 1 minus p hat over n, and the square root of all that is now going to be called something that we call the standard error. And so our z value now is going to be p hat minus p, so that actually hasn't changed in the numerator at all, but our standard error is now going to be used in our denominator, right, instead of our old standard deviation. So we're just going to plug in our sample proportion in place of our population proportion. And then we're also going to see something called alpha. This is called the level of significance. And this is basically the probability that your result is obtained by chance. And we're actually going to either set this value um, or the problem will basically give it to us directly or potentially indirectly. So we may have to solve for it slightly, but it's a pretty easy calculation. So our we call it a 100 minus alpha % confidence interval for our population proportion can be written kind of in this way. I know this might look like a little bit of a scary formula, excuse me, but it's really not too terrible. I just kind of wanted to walk through this to show you guys how we're going to get to our final answer. And our final formula for a confidence interval for the population proportion, just so you can kind of understand the logic that we're applying, right, to the formulas we've seen already. Right, so basically in this first line, we're just saying we're looking for the probability that our z value, right, our new z value is in between two other z values, right? A negative z value and the corresponding positive z value. This alpha over 2 just shows that this is the z value with alpha divided by 2 area under the curve, right, basically to the left, and this is actually going to be above. So yeah, we're doing an interval, right? We're looking for a value between two other values, right? We're looking for an area under the curve, kind of in between two values. And we want that area under the curve to be equal to 1 minus our alpha. So alpha will usually be values like 0.05 alpha. And we'll see this on the next slide. Usually equal to, could be 0.01, might even be 0.02 or 0.05. Right, so if alpha is 0.01, well, 1 minus 0.01, we could do it over here too, right? 0.01, that's 0.99, right? So we want the probability of our population proportion, right? Being between these two cutoffs to be equal to 0.99 or 99%, right? And this is something we would call just call it CL. This is the confidence level, basically. This value right here is our confidence level. How confident are we that the population proportion is in between these two cutoff values? And you can see these cutoff values are also dependent on alpha, right? So these are kind of directly related, right? The size of our confidence level or the our confidence level, how confident we are. If it's 99%, if we have a higher confidence level, that's going to change the cutoff values. Sorry, I lost my mouse all the way over there. If we, change our confidence level, and notice too, to increase our confidence level, you have to decrease alpha, right? So a smaller alpha results in a larger confidence level. If alpha is 0.05, well, 1 minus 0.05, that means your confidence level is 95%, right? So you have a lower confidence level and a larger alpha. So as alpha increases, your confidence level goes down. And we'll kind of see this a little more on the next slide, right? But this is kind of the idea behind this. So essentially, what we want to try to end up with in the middle of our interval, right, is our population proportion. That's the unknown value that we have, our population proportion. So we want to be left with that population proportion in the center of this interval, and we're just going to use some algebra to move everything else inside of this current existing interval outside of the middle, right? Put it on the lower and the upper end, right? So we're saying something is less than or equal to all of this in terms of z values. That's how we're starting off with, right? This is a z value. This middle thing is a z value. And this upper thing is a z value. So we have a z value in between two other z value cutoffs, kind of like in our problems previously, right? When we're asked about what's the probability that an IQ score is between 100 and 115, what did we have to do? We had to take 100 and convert it to a z value, take that 115, right, the larger cutoff, convert it to a z value, and then we had to find the area under the curve in between those two things. That's kind of the idea that we're using here, right? So if we start with this and we try to get the population proportion by itself, what can we do first algebraically, right, to make this essentially simplify, right, kind of go away? Well, we can multiply the denominator, which is the square root of p hat times 1 minus p hat, right? If we multiply this thing here in the numerator, then it basically just cancels out, right? So if we multiply the inside by a p hat times 1 minus p hat over n, right? If we add that up here with this difference of p hat times 1 minus p hat, what happens? This cancels out with this, right? But if we multiply it on the inside of this inequality, just like in algebra class, right? If you had x equals something and you were trying to get the x by itself, you would do something like this. You had to multiply it on both sides, right? So since we multiplied it on the inside, we have to multiply it here on this side and also on this side, right? So now you can see if we go down one row or step here, right? We've done just that. We've multiplied the inside by the everything inside the square root, and so we've also multiplied our lower inequality cutoff value, right, by that square root of p hat times 1 minus p hat over n, and we've multiplied our positive upper value here by the same thing, right? Pretty straightforward. So now we're almost there, right? We want p by itself. So now if we just subtract p hat, we can subtract p hat on this side and on this side. Positive p hat minus p hat just cancels that out, right? So the p hat goes away, but we need to bring over the negative p hat here. So we have negative p hat plus everything, right? This is a positive. And then we have negative p hat minus um, everything. And then we're left with negative p in the middle. So we have basically kind of one more step, kind of two that I've squeezed into one step here. So now what do we need to do? We can just multiply negative p, multiply that by negative 1, right? And a negative times a negative just makes a positive, right? So now we have positive p in the middle, but now we have to multiply this whole thing, right? Multiply by, it's not x minus 1, right? We're multiplying by negative 1, and then we have to multiply our upper side by negative 1. So what happens here if we carry this negative 1 through this whole thing and also this whole thing, right, on this side? Well, we have to carry it through, right? So we get a positive p hat here, and then we get a positive z alpha times all this stuff. And one more thing that happens is that we actually have to switch the sign or the side of our inequality. So this used to be a less than, now it's actually a greater than. So the greater than, the open face, right, is pointing to the positives. And then on this side, if we were to switch this inequality, we switch it back this way. And now we've got another positive p hat up, but negative 1 times a positive, right? Now we're going to subtract everything from our p hat, our positive p hat on this side. So now I've kind of flipped these inequalities, right? So my positive p hat plus my z alpha times everything, this is actually moved to this side of our inequality, right? You can see our positive p hat plus z alpha, and it's got the inequality open towards it, right? Just like we have here, our inequality is open towards our positive p hat plus this, and then the positive p hat minus our z alpha. This whole thing has just kind of been moved over to this side. And notice the inequality is closed off towards it, right? It's got the less than side pointing towards it. And we have that here. So we've got a positive p hat, and we're subtracting the z alpha times our standard deviation. So basically, positive population proportion is still in the middle. And I basically just flipped these around, including the inequalities, right? So we're saying that the sample proportion that we calculate minus all of this stuff is going to give us a lower cutoff value. And our sample proportion plus all of this stuff is going to give us an upper cutoff value, right? And so these two cutoff values are going to be the lower and upper values of our confidence interval, whether it be a 95% confidence interval, 99% confidence interval, or so on for our population proportion. And we're left with this pretty nice, pretty easy formula, right? Where we just take our sample proportion, we add and subtract, right? So when you add, you'll get, when you add something to the population sample proportion, sorry, you'll get a larger value here, right? And when you subtract everything, when you subtract all of this from our sample proportion, you'll get a lower value here. So this lower value will be the lower level of your confidence interval, and the added value will be the upper level, right, of your confidence interval. So you start with your sample proportion, add or subtract this z alpha divided by 2. So really just some z value either from our z table or from our calculator. We'll see kind of in the next slide how to find that a little more specifically. And then you just multiply that by the now standard error of your sample proportion, right? Um, so it ends up being a pretty easy calculation. We don't really need to worry about any of this from problem to problem, right? We can just use this final formula. But I kind of just wanted to walk through it with you all so that you could see kind of the reasoning behind it instead of just saying, hey, here's the formula. I just kind of wanted to try to explain how we're getting this formula right and why it works, kind of based on some of those same principles we've seen from chapter 5 and 17. So this is kind of what we are doing graphically, right? When we use this formula, and in this example, when our alpha is 0.05, remember this is a level of significance, and this is the probability that our answer is obtained by chance. So if our confidence level is 95%, what does that mean? That means if this were and I suppose it really is, this is a distribution of sample proportions, right? So it's a sampling distribution of sample proportions. We know that our population proportion should be at the center of this distribution of sample proportions. We don't know what that population proportion is, but when we set our alpha to 0.05, this means that we're setting our confidence level equal to 0.95 or 95%. And that again comes from this 100 1 minus alpha percent formula. So 1 minus this 0.05 if we're given alpha. One minus 0.05 is just 0.95, right? You multiply 0.95 by 100, that just moves the decimal over 2 places to the right. And so we know our confidence level is equal to 95%, right? So alpha will probably be given to you in the decimal format. So it's basically just converting that. You take 1 minus alpha to get the 0.95, convert it to a percentage. In this example, our confidence level is 95%. So what does that mean? Think back to chapter 17. If you have 95% of the area under the curve, then what 95% of all of your possible sample proportions fall in between these two cutoff values, right? And these are our Z alpha divided by 2, probably a little hard to see. Z alpha divided by 2, right? So if 95% of all of our possible sample proportions fall in between these two values that we can find, then what are we saying? We're saying that we're 95% confident, right? If our true proportion we know is at the center and has to fall between these two cutoffs, right? Because again, we know if 95% of all of our sample proportions are under the curve, then that's at least 2 standard deviations away, right? See how these lines are 2 of these hash marks away from the center. This would be +1 right? Standard deviation plus 2, right? Minus 1 standard deviation and minus 2 standard deviations. We're 95% confident that our true population proportion is 2 standard deviations below, 2 standard deviations above, right? We're 95% confident that that population proportion falls between these two cutoff values. Because why? Because we know 95% of our sample proportions will fall between these two values. Well, if 95% will fall in between those two values, that means 5%, right, have to fall outside. If the total area under the curve is 1 or 100%, that 100% minus the 95% we're confident about, this gives us that 5% alpha, right, that we're unsure about, right? So it would be rare, but it's possible the true answer could fall outside of our confidence level we're setting for ourselves because we truly don't know where the population proportion is, right? But we can use these principles to I don't want to say assume, but we can use these principles, right, to say we're 95% confident that it truly is that it is in between these values. Right. So if our alpha is 0.05 or 5%, that means we've got 5% left outside of our interval, right? And so this is where that divided by 2 piece comes in. We're not looking for a z-value where 5% of the area is left under the curve to the left and another 5% of the area is left under the curve to the right. We have to divide our alpha, our total area left under the curve outside of our interval, by 2 because it's again an interval. So there's going to be area left above and below, right? So if we have 95% inside, we don't have 5% below and 5% above, that would be 105%. That's more than the total area under our curve. If we've got 95% on the inside, we've got 5% left over. So we divide that by 2, and that means we've got 2.5% left above outside of our interval, right, that we're constructing, and 2.5% below our interval. So if we have a z-value here with 2.5% of the area under the curve left outside of our interval, I need to find this z-value, which is 0.05 divided by 2. So I need to find a z-value with 0.025 area under the curve to the left. And this, it will be a negative z-value, right? Because we're going standard deviations below our mean or our population proportion, right? So we can throw in a negative sign here just to remind us. And then this from the same exact kind of dividing that 0.05 divided by 2. I need to find a z-value with 0.025 area under the curve above my z-value to the right. And these values will actually be the same exact z-value, right? Because our normal distribution is symmetric, right? The value with 2.5% area under the curve to the left is the exact same as the z-value with 2.5% area under the curve above it. this value will just be negative and this one will be positive, which kind of goes back to the plus and minus, right? Will be adding and subtracting a positive number, right? So we really just need the positive because we end up adding it on this side and we end up subtracting it on this side, right? So that's how we would find the z-value, right? We could use our inverse norm function. If we know the area under the curve to the left is 0.025, we could just use that inverse norm. Let's do that really quickly. Function to find the z-value. Let's see if I can find it really quickly. If you can still see it after I share it. Don't know if you will be able to or not. Okay, I am going to stop sharing again just to make sure that you can see this. I'm going to pull up the calculator. So again, we know we're looking for a z-value cutoff. We don't know that z-value, right? But we do know the area under the curve to the left is 0.025. So when we know the area under the curve, but we don't know our z-value or our cutoff value, we use the inverse norm function. So we go to second and vars. We go down to option 3, INV norm for inverse norm, hit enter, and all we have to give it is the area under the curve, so 0.025, and we're in z-value terms, right? Which means we're in a standard normal curve. So that means our mean is 0 and our standard deviation of 1. We're going to ignore this tail. Not all TI-84s give you this option. Most TI-84s always default to that area under the curve to the left, right? So that's why I've put that 0.025 there. We're finding the lower z-value, right, on the left side of that graph that only had 0.025 or 2.5% of the area under the curve. Go down to paste, hit enter, and we see that the z-value that corresponds to that area under the curve is negative 1.9599. A lot of the times you'll see this just rounded up to negative 1.96. So if we go back to our drawing, slides, what does this mean? This means that the z-value here, that z alpha divided by 2 is equal to negative 1.96. And here it's equal to a positive 1.96, right? So if this was a standard normal distribution, right, then we'd be centered at 0. One standard deviation to the right exactly would be positive 1. One standard deviation to the two standard deviations, I'm sorry, would be exactly 2. So we're actually just 95% under the curve. Is just actually a little bit less than exactly 2 standard deviations to the right or left of our standard normal curve. And so actually what is really great about population proportions is these z-values actually never change, right? The normal distribution, the standard normal distribution, it's always centered at 0. It always has a standard deviation of 1. So these z-value cutoffs that we find, they never change, right? So for every problem now, where we're asked to find a 95% confidence interval for the population proportion. Our confidence level is 95%. We know alpha is 0.05, right? This alpha here. So we know alpha divided by 2 is 2.5% or 0.025. And we know that the z value is always going to be this positive and negative 1.96. So we never have to really find this again for the 95% confidence interval question about a population proportion. And then similarly, right, when we get to a problem where we're asked to find a 98% confidence interval, we just have to find that z value once, right? Write it down in your notes and you never have to find it again. You'll just kind of know going forward what it will be. We kind of did this on that last slide. We found the negative 1.96 and positive 1.96. If that didn't make, if the way we found that 0.025 didn't really make sense to you, there is this other kind of formula that you could use to find the z alpha over 2. You go back to inverse norm, which we did if you're given the confidence level. So if we're given a 95% confidence interval, right? Find a 95% confidence interval for the population proportion. You can just divide that by 2 and then add, a 0.5. If this was, in a decimal format, which is kind of how we input our numbers, right, into our calculator. We don't usually do 95 for 95%. We do the decimal form. So if we do 0.95 divided by 2, we get oops, go back. 0.95 divided by 2 is 0.475 plus 0.5. So then if we add the 0.5, we get 0.975. And so notice that if we're plugging this into the inverse norm, we're looking for 0.975 area under the curve to the left. So we're really finding this positive z value over here. In the last slide, right, I plugged in 0.025, the area under the curve to the left of our lower cutoff value, and that gave us negative 1.9599, or that negative 1.96. Right here, we're adding the 0.5, so we're actually finding this z value over here. You might be asking, well, why is it 0.975 if it's a 95% confidence interval? It's because if you're finding the area to the left of this upper value, you need the total area under the curve inside of your interval or your limit, which we know is 0.95, but you're also finding everything to the left, right? You've got one value, so you're going all the way to the left. So you're really adding this 0.95 and this 0.025 to get the 97.975, right? So 0.95 plus that 0.025 out here to the left is how we're getting this 0.97, right? So this is kind of just a shortcut of a trick to get the area under the curve, right, of your higher z value cutoff based on that alpha level that you've got. So we can do this as well, right? If we plug 0.975 into our inv norm. You can go back to second and vars, go back to option 3 for the inv norm. Instead of 0.025, now I'm going to plug in that 0.9. Whoopsies. I'm going to plug in 0.975. We're still under a standard normal curve, right? We're talking about z-scores. So I don't need to change any of this. The area under the curve to the left of 0.975 is exactly our positive 1.9599, or that positive 1.96. And so this is what I was talking about, right? Whether you find the area under the curve to the left of your lower z value, this 0.025, or if you find the area under the curve for your upper z value, in this case the 0.975, those z values, they're the same numerically, because of the symmetry of the normal distribution. One is just negative and one is positive. So finally, in our last slide, right, we kind of want to wrap these answers in a nice conclusion. So we say we're 95% confident that the true proportion is between blank and blank, right? Whatever, when you plug in all those numbers into that formula, and you get a lower and upper value in your confidence interval. Those numbers go here and here. And we'd say we expect 95% of all possible confidence intervals calculated with that specific sample size in to contain the true proportion of the population. We don't just directly say there's a 95% chance of a particular value in the interval. And this is because we've only calculated one confidence interval, right, with one specific sample proportion. Whereas we know there's a distribution, right, of many different sample proportions that you could get depending on the sample that you take. We could take many, many, many different samples from the same population, and each of those samples could give us a different sample proportion, right? So since in this example, we've only taken one of those sample proportions, we can say, well, if we were to take another sample, right, calculate another confidence interval, there would be some overlap, right? They might not align perfectly. But if we could take all the confidence intervals possible, we'd expect 95% of those to line up, right, and contain the true population proportion. Yeah. So in the next video, we will work an example and put this into practice.